Hello, my name is Daisuke Nishiyama from Preferred Networks. Here, I would like to present our paper on how to test planning algorithms for self-driving cars. The title of the paper is Discovering Avoidable Planner Failures of Autonomous Vehicles Using Counterfactual Analysis in Behaviorally Diverse Simulation. This is a joint work of Preferred Networks and Toyota Research Institute, or TRI. When we develop a self-driving car, it is necessary to test its safety, but it is a hard problem. One obvious option is to deploy the system into an actual car in this real world and test it. But this is costly with very limited coverage, while being challenging to guarantee the safety of drivers and environments. This kind of real-world testing is of course ultimately necessary, but as a preliminary step, to use simulation can be very helpful. On the simulator, we can easily change modules and environmental elements such as the courses and the placement of surrounding vehicles. In this paper, we focus on testing the planning algorithm for self-driving cars and propose one way to do this efficiently when using simulation. Recently, a number of traffic simulators have been developed for this purpose and have been used in practice for testing. For example, CARLA, SUMO, or FRUIS are popular ones. These simulators mainly focus on simulating vehicle dynamics and sensors such as cameras and lidars. However, the behavior of the vehicles are basically prepared by the simulator user. In that case, if we prepare two simple models such as random models or simple rule-based models, they wouldn't be able to cover the diverse and complex traffic scene scenarios in the real world involving edge cases and rare events. When testing in the simulator, we need to somehow create scenarios that include such edge cases and rare events. This study proposes one way to do that. Also, in previous work, there are some attempts to test safety in a simulator by making vehicles and pedestrians behave in an adversarial way. For example, in a 2018 paper by Tankori et al., they did an experiment of adversarial testing with a simple manually fixed traffic scene. Such a test would work well for systems like emergency braking, but it is not suitable for testing general planning algorithms, since it is possibly missing diverse, realistic, cooperative, and safety-critical cases. Also, a 2019 paper by Corso et al. Discusses how to generate test cases that actually induce dangerous movements of the ego vehicle. If we can find cases of such dangerous movements, it will be relevant for the development of planning algorithms. This study has similar motivation to ours, but in this study, basically they have to train an RL agent again every time the test target is changed. Also, they trained two models separately for inducing dangerous movements and for detecting diverse failure cases respectively. Our study establishes finding both relevant and diverse failures at the same time, and it does not need to train again even when the test target is changed. Our main motivation and contribution in this study is how to address both these two important factors in planner testing using simulation. That is, a way to prepare the diverse and complex behavior of surrounding vehicles. This is the first contribution of this paper. We show that this allows us to detect planner failures that cannot be detected in an environment with only vehicles with simple behaviors. Furthermore, we show that many of the failures detected by this method are relevant for planner development. This is our second contribution. Here, a relevant failure means that it could have been avoided if the planner somehow worked well, and it would be useful feedback for the planner developers. In the following, I'd like to show you the specifics of our work. The first contribution of our work is that we propose a way to create a diverse testing environment. To explain it, first I'd like to introduce the traffic simulator we used. We developed a simple traffic simulator to evaluate our proposed method. The simulator looks like this figure. It simulates a typical intersection with two lanes of roadway intersecting each other with no traffic lights. Vehicles must pass through this intersection while observing each other's movements. We use policies trained by reinforcement learning for other vehicle agents. Thus, they are not just rule-based but learn behaviors for a complex intersection. So, this simulator is a complex, interactive, multi-agent traffic scene simulator. Next, here are the scenes and the scenarios used in the actual experiment. We used the scenario at the intersection, and we considered these two types of movements of other cars. We will call these right turn and crossing respectively. As the policy of the other vehicle agent, we use a set of diverse policies which are generated by our proposed method, and we also use a set of policies with less diversity as a comparison. We used results of our group's previous work to produce a diversity of policies for other vehicle agents. This behaviorally diverse traffic simulation method creates diversity by setting additional rewards for learning a set of policies in reinforcement learning, and it uses a method of selecting a practical number of policies from that set while maintaining diversity. This video visualizes how the obtained various policies control the agent. We can see that diversity has led to qualitative differences in the trajectories, in this case yielding or not yielding for oncoming traffic when making a right turn. Using this method, we can create massive numbers of interactive and diverse scenarios automatically, so that there are a lot of rare cases and edge cases included there. Now, I would like to move on to the second contribution. It is a proposal of a method to detect failures that were relevant to the development of planner algorithms. We define a relevant failure as one that could have been avoided if the planner has planned their moves better. Here, a failure simply means a collision with another vehicle. In the following, we will call it an avoidable failure for clarity. Avoidable failure can be beneficial to developers as it provides feedback that the planner algorithm has room for improvement. We will refer to failures that are not avoidable failures as unavoidable failures. This is a failure that cannot be avoided no matter how well the planner works, and is relatively less beneficial. Well, how could we tell if a failure is avoidable or not? What we propose here is a way we call a counterfactual analysis, as the title of the paper suggests. This means that when a collision is detected, we rewind some time back from that moment and try to find a way to avoid it. This is the second and main contribution of our paper. This is something that cannot be done in the real world, and it would be a unique method by using a simulator. We also propose two methods to try to avoid collisions after rewinding: planner-specific and generic methods. The first, planner-specific, is a direct method, and it changes the parameter of the current planner algorithm in various ways to try find a set of parameters that can avoid a collision. For this search, we used Optuna, a hyperparameter search tool. In this way, if a collision avoidable parameter is found, developers can set it up in the planner immediately, so it would be useful feedback for them. Second, generic approach considers a wider range of action possibilities. This replaces the planner algorithm itself with an entirely different, more safety-oriented one, and checks if the collision is avoidable when acting with maximum safety within the vehicle dynamics. The replacement algorithm is based on previous work of Maeda et al. 2019 that runs safe policy through reinforcement learning. And here is a description of the test target used in the experiment. We used a model based on the Intelligent Driver Model (IDM) as a planner algorithm. The IDM is basically just an algorithm that only follows the leading car, and it is not suitable to be applied directly to scenes where there is interaction with multiple vehicles, such as at an intersection. So we have added a simple rule-based algorithm to this to determine which vehicle to follow. This will allow the test target to well drive through a complex intersection scene. We ran the simulation and counted failures in the above environment and settings. 50 different policies were used for right-turn and crossings. For each policy, 300 simulations were performed by randomly changing the initial position of the ego vehicle and other vehicles. Therefore, a total of 15,000 tests were conducted for each scene. The result shows that we can detect more avoidable failures by using the diverse policy set. Especially, we detected collisions with the car 1 only when using the diverse one, and this implies an effectiveness of our method of finding failures in the planner testing. It is also important to note that a variety of failures are detected. We analyze the failures by the angles, locations, and overall state of the environment at the time of the collision. These figures are visualizations of that, and these are collision angles, locations, and whole collision state projection by TSNE, respectively. And due to time constraints, let me go through them very briefly. Collision angles have wider distribution for the diverse policy set. And same for collision locations for the diverse policy set. This is a TSNE analysis of the whole state, including positions, velocities, accelerations, steering angles, and it also shows that the diverse policy set exhibits clusters of the collision state which don't appear in the less diverse one. That is a brief description of the results of the experiment, and here let me again present a summary of this paper. We proposed a method for planner testing in a complex, interactive, multi-agent simulation environment. In the simulation, agents showed a wide diversity of behaviors. We defined the concept of the avoidable failure, which is relevant and useful for planner development. We used a method of the counterfactual analysis to define it, and we showed that diverse behaviors can find more avoidable failures. Finally, I'd like to talk about future directions. This time, we tried two traffic scenarios, that is, right turn and crossing, but our method is very general, so it would be great to apply it to various complex situations. One possible way is to expand maps and environments, for example, to include traffic signals or pedestrians and so on. And another way is to apply our method to some recent practical planning algorithms. We believe that such trials will give us further perspective on planner testing. That's all for the presentation. Thank you for your attention.